So usually we think of those as the same thing. Heat and temperature are like in everyday life. We would think of those as the same thing. They are completely different in physics and chemistry and biology. They're very different values. They represent very different things. One of the main things that we want to talk about with heat and temperature is state changes. As you can see, ice cubes melting. That's like a very big topic in heat and Q, right? And, the next slide. Heat is actually represented by the letter Q, and it's a lowercase q, right? Which is a little bit, which is completely different from the uppercase Q, which we talked about before. So don't get those two confused. And delta T, which is just change of temperature. Okay. A very common formula you may be asked about it on the MCAT is Q equals MC delta T. Most people say Q equals MCAT because the delta looks like an A, right? So Q is heat, M is mass, C is heat capacity, and T is temperature. In this case, temperature could be Kelvin or Celsius. It doesn't matter because to get from Celsius to Kelvin, you add 273. So if you look at the math, it doesn't actually matter if it's Celsius or Kelvin. The difference in the temperature is going to be the same, whether it's Celsius or Kelvin. Yeah. C is a measurement specific to each substance, and it determines how much heat is actually required to increase the temperature by 1 degree, right? And this can be 1 degree Celsius, 1 degree Kelvin, they're the same again. It is in units of joules per gram times Kelvin. Again, I use Kelvin here. Could be Celsius. It's the same. So essentially, it would be different if you did Celsius versus Kelvin. The number would be, I think, a little bit different, but it's like you can use either, right? You don't have to convert all the time. Depends what they give you and what units. It would be easier, right? So what this number actually means is, and you can look at this in the units, if you had 1 gram of, say, any substance, say like metal, some kind of metal like an iron ball or a rubber ball and like a plastic ball of the same size that weighed 1 gram exactly, all 3 of them, how much heat would you have to apply, how much energy, heat is in the form of energy, how much energy would you have to apply to each ball to get it to increase by exactly 1 degree in temperature, right? And this can be 1 degree Kelvin or Celsius, and that determines heat capacity. A number that has a high heat capacity would be something like water, right? Water doesn't change its temperature very easily, right? You need to apply a lot of heat energy to water in order to get it to change temperature, right? And you can look at this compared to something like a metal, like iron. You can heat up iron very, very easily, and that's why it has a very low heat capacity. You need very little joules of energy to get it to increase by 1 degree, right? So if it had, say, a heat capacity 5 times lower than water, if you apply the same heat or the same heat or the same energy to a piece of water and a piece of iron, the iron would go 5 times higher. It would change the temperature 5 times as much as water, right? It would change the temperature much more easily. You can get this from the name heat capacity as well. How much heat can this substance hold before it changes temperature, before it gives up and changes temperature by 1 degree, right? Higher heat capacity can absorb a lot of energy, can hold a lot of energy before it changes temperature. Low heat capacity is not. Anything with a low heat capacity is a very good conductor of heat. Again, any kind of metal or anything like that, iron, steel, copper, whatever. Anything that is a poor conductor of heat, water is not very good. Air is very, very bad. So something like an air like substance is very bad for conducting heat. So it has very high heat capacity, right? And like I mentioned, Q is measured in joules, right? Okay. Next, I want to ask, yeah, if the heat capacity of water is 4.18. if anybody wants to know. I wanted to ask if anybody would be able to tell me in the chat, actually, and I want to ask the chat this. We don't have a poll question. I just want to ask, some people would know. If you have a pot of boiling water, do you know what the temperature of the water is? So if you say you had a pot of boiling water and you boiled it for 6 hours, and you had a huge pot and you were boiling it for 6 hours, do you know what the temperature of the pot, of the water inside the pot would be? If you're boiling it for like 6 hours, right? Right, okay. So a couple people are saying 100 degrees Celsius, and that's exactly right, right? You would think that you have the pot on for 30 minutes of boiling water, the water starts boiling. Say it reached 100 degrees, because you know that's when the water starts boiling. You keep it on for another hour, you added in a lot of heat, right? So you'd think the temperature would increase, right? You kept it on a fire for a very long time, right? And from it was boiling. But actually it wouldn't change, right? If you have a pot of boiling water for 30 minutes on a heat stove, or if you have it for 6 hours on a heat stove, the temperature of the water doesn't change unless all of the water is gone, unless the water all boils out, right? As long as you have a source of water, it'll always be 100 degrees Celsius. And we're going to explain why that is right now. So if you see this diagram, on the x-axis, there's energy. On the y-axis is temperature. If you start at point A, so solid, say like ice. We had a very low temperature, we had ice. You put it on like some kind of heat source, like let's say a stove, right? And then you apply the energy, turn on the stove, you apply the heat or the energy from the stove onto the ice. As you expect, the temperature of the ice would rise gradually, slowly. That would get us this blue line up until point B. Then it would reach, the ice would reach 0 degrees Celsius, which is the melting point of ice. And then at this point, it would stop raising temperature, and you would go into this red area, the phase change, which is called melting. During this phase change, you can keep the stove on, and it will still be producing heat, and it'll still be transferring heat into the ice, but the ice wouldn't change temperature. It would remain at 0 degrees Celsius. Where would that energy be going? Well, that energy would be going into actually melting the ice, turning the ice into water. Ice can't just turn into water on its own. It needs a source of energy, like an outside source of energy to do that, right? So if you notice at the red line, all of the ice would be slowly melting. At this halfway point in this red line between B and C, halfway, half of the ice would have melted into water, half of it would still be ice, half of it would be water, right? Then you progress further and further, and then by the time you reach point C, all of the ice will have melted into water. Once you no longer have ice and you have only water in the liquid state, any additional energy or heat from the stove that you add onto it would just increase the temperature of the water, right? Because the water is already there, it's already water, it's not ice anymore. Now adding heat or energy to it would raise the temperature rather than change state. Okay, then you reach point D, which is 100 degrees Celsius for water, right? The boiling point. Your water starts to boil. This red part, again, would be the phase change. You keep it on the stove, and then it would, all of the energy from the stove, all of the heat would go into changing the water into a gas. None of it would go into increasing the temperature. That's exactly why if you have a pot of boiling water, no matter how long you keep it on the stove, as long as you have water in the pot, it will always be 100 degrees Celsius, right? As soon as you run out of water, the pot will, all of the food that's in the pot, let's say you have like a potato in there, all of the heat would be transferred onto the potato and it would burn because it's not temperature controlled anymore at 100 degrees Celsius, right? But as long as you're in this red zone of having water in the pot, all of the energy from the stove and all the heat would be going into changing it to gas form, any remaining water into gas form. Then once you reach point E, all of the water is turned into gas. Then you add more heat into the gas, and the gas will increase temperature again, right? And you'll eventually get to point F. Okay. And I wanted to ask you guys actually, what do you think? So we had, say, water. Like, go back to my example of a boiling pot of water. We have delta H, delta S, and delta G. At the boiling point, 100 degrees Celsius, do you think, so at this area, this red area, do you think water that's has just begun boiling would have a positive or negative delta H, a positive or negative delta S, and a positive or negative delta G, the transition of water into water vapor or gas when it's boiling at the boiling point, which is 100 degrees Celsius? If you want to, guys, want to put the answers in the chat, this is a full question. Just do you so first let's start with delta H. Do you think you would have a positive or negative delta H to go from water to gas at 100 degrees Celsius? Okay. A couple of people will put in positive delta H. Okay. And okay, I agree. It will be a positive delta H. So how did we know that? Well, I just told you that in order to go from a liquid to a gas, you actually need energy input, heat input, right? You need to keep the stove on for it to provide heat and energy to the water. Otherwise, you turn the heat off, you turn off the energy supply, it just stops boiling, right? This transition stops. What that means is that in order for the reaction to proceed, you actually need an energy input. You need it's endothermic, right? You need to absorb energy. Endothermic reaction always has a positive delta H, right? A positive reaction always has an endothermic reaction always has a positive delta H. We know that this is endothermic because it has to absorb heat. It's positive. Now let's see with S. Do you guys think it would be a positive or negative delta S, the transition from water to water vapor? Okay, so this one's a little bit more mixed, and let's see. Okay, so this one's a little bit more mixed. Some people are saying positive, some people are saying negative. The correct answer is actually, it would again be positive. And let me explain. So we know that gases always have more entropy than liquids. You can think of it this way first. The end result on the right side is the end result. It's gas. On the left side is the initial. So we'll keep it like this level. Sorry, this is the end. This is the end. This is the beginning. The entropy levels. Gas is always higher than a liquid, right? You know that the entropy of a gas is always higher than the entropy of a liquid. So the end result, the ending entropy is higher than the initial entropy of a liquid, right? Delta S is the change. The change was by this much, right? If I had that much, the change is by this much, and it's in the positive direction, right? The ending is more than the starting. If the ending is more than the starting, that means you had a positive change. That means you increased by a positive amount, right? We also know that unlike with enthalpy or H and G, enthalpy and Gibbs free energy, a positive delta H is actually favorable. A negative delta H is not favorable, right? We want more entropy at the end. We want a higher S at the end. So we want a positive delta S, right? We always know that, again, a gas is always more entropically favored than a liquid. So it would have to be positive, right? And going from a solid to a liquid, it would be the same thing, right? Delta H would be positive, delta S would be positive. Now, we know that delta H positive, delta S is positive. Do you guys have an idea of what delta G would be? And I'll explain this all again because we're almost at the end. So I'll explain. I'll go more in detail. But do you guys know what delta G would be right now? If we want to move on from this a little bit, in the chat. And I think it's an agreement, at least for delta G, it's an agreement. And I actually like the way that somebody put it in the chat, negative at high temperatures. And yes, so because they are conflicting, delta H is not favored, delta S is favored. They're conflicting. Like I said, at high temperatures, delta S wins, or delta S gets determined favorability. Since delta S in this case is favorable, at high temperatures, delta G will be favorable or negative, whereas at low temperatures, delta S would lose and delta H would win, which is, it would be unfavorable, so delta G would be not favorable. And that's what actually the melting point is. The melting point, or the boiling point, I should say in this case, because we're going from liquid to gas, the boiling point is the temperature when S starts to win out over H. The boiling point and the melting point are the lowest temperatures in which delta G is negative, right? If you go even 1 degree lower than the melting point or the boiling point, delta G is either 0 or it's positive, right? It should be positive, right? Once you reach the boiling point or the melting point of anything, that's when that's the first temperature, that's the lowest temperature that delta G is negative, right? That's why once you reach that point, it starts boiling or melting. Okay, so this is a good exercise. I'll go over it again in a little bit if anybody's still confused, especially about delta S. Okay, and the same thing would apply if I asked you about the melting point instead of the boiling point, going from a solid to a liquid. Delta H would be positive, delta S would be positive, delta G would be negative at the boiling point.